Hey everyone, in this video I would like to discuss Riemann sums. And the first thing I want to do is just explain what a Riemann sum is. So to begin with, a little bit of review. So far, the way that we have discussed how to find the area underneath the graph of a function is by summing the areas of a bunch of rectangles. Essentially, we find the area of these rectangles and we add them all together, and it gives us an approximation for the area underneath that curve. Using calculus, we let the number of rectangles become unbounded or approach infinity. So we use the limit as n approaches infinity, where n is the number of rectangles, or it's the number of subintervals. While we were doing that, we also specifically said that we want the heights of each of these rectangles to either be the absolute minimum or the absolute maximum within each subinterval. Well, that's where Riemann comes in. So Riemann sum is named after the German mathematician Bernhard Riemann, and he basically figured out that it doesn't matter if we use the absolute minimum, the absolute maximum. Actually, it doesn't matter what point we use in each subinterval. This is because if we use the absolute minimum, it gives us the smallest estimate for the area. If we use the absolute maximum in each subinterval, it gives us the biggest approximation for the area. And then using the squeeze theorem, as these limits approach infinity, we can show that it doesn't matter what point we use. We can pick out any point within each subinterval, and we should be able to get the same answer. So Bernhard Riemann, he was able to change up the summation a little bit and show that, one, it doesn't matter what height we use for the rectangles, so it doesn't matter what x value in each subinterval we use, and it also actually doesn't matter how big each subinterval is either. So when we see the phrase use Riemann sums, basically all that's telling us is we're going to be adding together the area of some rectangles. The intervals don't have to be the same size, and it doesn't matter what point we use within each subinterval. So I would like to take a look at an example where we talk through some of that process. So my example here says for the function f of x is equal to x squared minus 3, and we're looking at the interval from 0 to 6. Let's partition that interval into 4 subintervals, 0 to 1, 1 to 2. Both of those have a length of 1. 2 to 4 and 4 to 6. Both of those have a length of 2. So as you can see, these subintervals don't have the same size. And form the Riemann sums for which u sub I is the left endpoint, u sub I is the midpoint, or u sub I is the right endpoint. So a couple of things. First, the notation u sub I. So because in a Riemann sum, it doesn't matter which x value in each subinterval we use, instead of using c sub I like we did in the last examples, we can just use u sub I to represent any point within that interval. The second thing, when we're using Riemann sums, it is most common to either use the left, the midpoint, or the right endpoint. So I already have this function graphed as well. So let's just take a look at this. So our intervals, we are looking at from 0 to 1. We have from 1 to 2, from 2 to 4, and from 4 to 6. And in each case, we're going to be looking at the area of a rectangle within that interval, and then we're going to add those areas together. So for the first example here, the first part of this question, we are going to be using the left endpoint of each interval. So in the first interval from 0 to 1, we want to be using the point at 0. For the second interval, we're going to be using the point at 1. In the third interval, we're going to be using the point at 2. And then the last one, we're going to be using the point at 4. Now, when we're figuring out Riemann sums, my notation that I'm going to use, we're still going to use capital sigma to represent the summation. And then we're going to go from I is equal to 1. And in this case, n is going to be 4 because we have 4 subintervals. And we are adding together the areas of rectangles. So we have f of u sub I. This represents the height of each rectangle, and u sub I is any point within each subinterval. And for letter A here, this is going to be the left endpoint. And then we are going to multiply this by the width of each of these rectangles, which is delta x sub I. And I am using x sub I here because the widths of the subintervals may be different. So we have 4 subintervals here, and let's just make note of how wide each of these are. 0 to 1, this has a width of 1. 1 to 2 is 1. 2 to 4, this has a width of 2. And then 4 to 6, this also has a width of 2. So now we're going to sum together the area of all these rectangles. So going through, for our first left endpoint, we have f of 0. And then multiplying that by the width of that interval, so times 1. Plus f, the left endpoint in the second interval, so f of 1. Multiplying that by the width of the second interval, which is also 1. And if we just keep going, we have f of 2 times that width of 2, and f of 4 times that width of 2. So let's go through and evaluate each of these. So 0 squared minus 3, we have negative 3 times 1. 1 squared minus 3, that's going to be negative 2 times 1. F of 2, 2 squared minus 3, so that'll be plus 1 times 2. And then our last one here, f of 4, so 4 squared minus 3. 16 minus 3 is 13 times 2. And now multiplying these together and then adding them. So we have negative 3 plus negative 2 plus 2, and then finally plus 26. That's going to give us a grand total. So the 2's cancel out, and we end up with 23. Now let me just draw in these rectangles so we can take a look at what we were figuring out. So the first rectangle has a leftmost endpoint at 0, and it's covering that interval from 0 to 1. Our second rectangle is going from 1 to 2, and it has a height down at f of 1. Our third rectangle from in the interval of 2 to 4 is going to be pretty low here because it has that height of f of 2. And then our last one going from the interval on 4 to 6, it's going to look like this. So taking a look right away, we can tell that this Riemann sum doesn't actually represent the area under this curve. This curve, x squared minus 3, actually it's not non-negative everywhere, meaning part of it is beneath the x-axis. And because of that, this Riemann sum doesn't actually represent the area under the curve, but it is giving us an approximation that's going to lead us towards the integral. So this was using the left endpoints. Now let's use the midpoints, and we're going to do the same exact process. Now for the midpoints, let's see, so the midpoint in this first interval is going to be a half. The midpoint in our second interval will be 3/2. The midpoint here will be 3, and then lastly, this midpoint will be at 5. So these are going to be our midpoints. But we want to do the same thing, so we're going to summation. We're going from I is equal to 1. We have 4 subintervals. In this case, each f of u sub I, the u sub I is going to be the midpoint of the interval. And then we're going to multiply that by delta x sub I, which is the width of each subinterval. So going through our first one, so we have f of 1/2 times the width of 1, f of 3/2 times the width of 1 also. Our third subinterval, f of 3 times a width of 2. And our last subinterval, we're going to do f of 5 times the width of 2. All right, so let's see what we get here. 1/2 squared is 1/4. Minus 3 is going to be -2 3/4. 3/2 squared is going to be 9/4. And subtracting 3, we get -3/4. And that's times 1. F of 3, so 3 squared is 9 minus 3 is 6 times 2. And lastly, 5 squared minus 3, so 25 minus 3 is 22 times 2. And adding these all together, we're going to end up with a total of 52.5, or 52.5. So now, just taking a look at what this one would look like. So we're going to each midpoint. So we have at 1/2, at 3/2. The midpoint from 2 to 4 is going to be at 3. And then the last midpoint is at 5. And now let's draw in these rectangles. And then we can compare that to what our first one looked like. So from 0 to 1, and we go up to that midpoint. From 1 to 2, to that midpoint. Here we're going from 2 to 4. And then lastly, from 4 to 6, we end up with rectangles that look like this. So again, we do have some that is below the x-axis. So again, this doesn't necessarily represent the area under the curve, but we are getting a better approximation as to what is happening between the curve and the x-axis. And let's just go through our last one. Here we're going to be using the right endpoint. So we're going to take our sum. We're going from I is equal to 1 up to 4 for 4 subintervals. F of u sub I times delta x sub I. And now we want to use the right endpoint. So for our first subinterval, that's going to be f of 1 times 1, which is the width. F of 2 times 1 for the width of the second subinterval. F of 4 times 2. And our last one, the rightmost point is 6, and that also has a width of 2. So for the first one, 1 squared minus 3, it's going to be -2 times 1. 2 squared minus 3 is going to be 1 times 1. F of 4 is going to be 16 minus 3, so 13 times 2. And then our last one, 36 minus 3, 33 times 2. So we have -2 plus 1 plus 26 plus 66. Which is going to give us a total of 91. And to finish up here, let's draw in these rectangles as well. So we're going to the right endpoint on each interval. So at 1, at 2, at 4, and at 6. And drawing in these rectangles, now in this case, it looks like we only have one rectangle that is beneath the x-axis, but this is still just representing the sum of these rectangles and not necessarily the area under the curve. And in this case, using these right endpoints, it does look like we have quite a bit of extra area, especially with this last rectangle, which is quite a bit above the graph of our function. But to summarize, that's what a Riemann sum is. A Riemann sum, we are adding together these areas of these rectangles. It doesn't matter what point we use within each subinterval. Most often we're going to use the left endpoint, the midpoint, or the right endpoint. And it actually doesn't matter how wide each subinterval is either. So Riemann sum, you're breaking up the interval into subintervals, you're finding the area of these rectangles, and you're adding them together. And finally, as you can see, and hopefully you can make the connection as to what we were doing before, the more rectangles we use, the more accurate this is going to be. And if we were able to let the number of rectangles approach infinity, we would be finding the area under the curve as well.